All right, my name is Stephanie Lane. I'm a research staff member at the Institute for Defense Analyses. This is a mini tutorial statistics boot camp, but a little bit less dauntingly. I'd rather just sort of call it a statistics refresher. So if it's been a while since you had a statistics class, or maybe you do a lot of analysis in your day-to-day job, but it's been maybe a while since you had a refresher on kind of the basics of why do we do this and what does it buy us, that's really what this talk is aimed for. If you have a PhD in statistics, or you are a statistics instructor, I hear the other sessions right now are really interesting. I will not be offended at all if you take your leave. So make sure this is, here we are. So the outline of the boot camp today, we'll go through these steps basically. We'll sort of start at the basics of summarizing and simplifying data. The point here is really just to make sure that we're all working kind of from a common vocabulary. So with that, when I say things like continuous variable, discrete variable, nominal scale of measurement, you know what I'm talking about. Point and interval estimation is where we'll go next. Why do we use estimation, and how is estimation different from the kind of standard process of hypothesis testing? The foundations of statistical inference, I think this is the thing that can get lost sometimes when we go to R or JUMP or Excel or our software program of choice and we start analyzing data. Sometimes it's these foundations that get left behind a little bit. So I want to make sure we brush up on that. Next, the process of hypothesis testing. I'll warn you that this is perhaps the most textbook-like portion of the talk, but I'll try to keep it interesting for you. Finally, common statistical tests, and then close with a few tips. So to kind of orient how we feel about this topic, I know very few topics that are as polarizing as statistics, right? So you know how Google sorts these, right? They sort the things that people search the most. So this is a sample from the population of how people feel about statistics. So maybe it's hard, boring, important. Hard to say. I didn't understand that at first until you try to say the word statistics over and over again, and it actually is kind of hard to get all those syllables out. So pro tip, don't think about that when you're trying to say it, because you'll stumble over the word like I probably will. So if statistics to you are hard or boring, hopefully the next 90 minutes will change that, especially if they're confusing. I will say I do appreciate this note about being important for public health. I suspect that's the population of biostatisticians who are Googling this. So before we get in, one last chance for anyone who is a statistics expert to hit the deck. All right. So thinking about variables, again, the point here is really to provide kind of a framework of vocabulary. So a variable is a characteristic, fundamentally, that is either observed or manipulated. In operational testing, we frequently manipulate factors, right? And a factor is just another name for a variable, but particularly one that we are experimentally manipulating. But sometimes there are things that we can't actually manipulate, right? With a system, maybe it's just something that we can't get our hands on to manipulate, so we just observe it. With human data, this happens a lot. There are many things with human beings that we can just observe. We can't manipulate them. I can't manipulate certain fundamental things about you as an operator. And we frequently think about variables in terms of them being continuous or discrete. And so just making exactly clear what I mean by that, continuous variables have fractional amounts. So height is an example. If you ask a 5-year-old how tall they are, they will quickly demonstrate this because they will give you that height to the last fraction of an inch to demonstrate how tall they are. Discrete variables instead are distinct, separate, countable values. So these are things like the number of missiles, the number of human beings sitting in this room, perhaps the crew, rank of a certain crew, what their sort of relative status is. For these variables, it doesn't make sense to add them up and divide by 2, right? We can't take fractions. Fractional amounts don't make sense. And the reason I emphasize this is because the type of variable that we have has implications for everything downstream. How we describe it, how we summarize it, how we analyze it, how we visualize it. And so it's important to understand what type of variable we're dealing with. So the last of my vocabulary blast is we don't just think about a variable in terms of what its type is, but also in terms of its scale of measurement. So as you visually go through this table, consider that at the top of the table we have the least amount of information, and as we move down the table we add more information about that variable. So something that is nominal is just a named category. So if we have a vehicle, the wheel type is a nominal scale of measurement. If it's tracked or wheeled, we just have information about a named category. In the social sciences, an example of this would be college major. Were you a biology major? Were you a physics major? Were you an engineering major? It's a nominal variable, each of named categories. They don't have any inherent order, no matter what physicists will tell you about them being number 1. Nominal. At least number 5, exactly. Next, we move to an ordinal scale of measurement. So here we still have named categories, but they have some inherent order. Place in a race, first, second, third. If Heather places first and I place second, we don't know whether she beat me by a second or by an hour, right? We just know that she was relatively ahead of me. So we have more information than we had with nominal, but still not information about the distance between those values. Interval information still is ordered, but now we have equidistant values. So a good example of this is temperature measured in Fahrenheit or Celsius, because we have numbers that have equal values, equal intervals between them. Finally, ratio provides the most information. We have ordered values, they're equidistant, and there's a real 0 point. Right, so a good example of this is something like distance. So if I'm 6 feet away from something and you're 3 feet away from something, then I'm twice as far as it than you are. And so with ratio data, we can literally form ratios of those numbers. And so it's helpful to note that when possible, we really prefer interval and ratio scales of measurement because they provide more information. If we collect something as a ratio scale, we could always go back to a coarser measurement, right? So if I measure something as distance in meters, but it turns out I really just needed to know whether something was near or far, I could always get back to that. But if for some reason my checklist only had a box for near and far, I would have a much harder time later getting that information back. So when we move to simplifying and summarizing our data, what are our tools for that? So there are 2 tools that we use a lot. One is broadly called central tendency and one's called variability. So central tendency aims to describe what's called the centrality, or sort of the typical score of a distribution. So central tendency means that we take our scores, our variable information, we try to come up with one number to represent that. With variability, we're trying to quantify the spread of a distribution, or sort of how far away a typical score is from the center. So common measures that you've probably come across before, and you probably report these, are things like standard deviation, variance, range, interquartile range. These are all ways that we can describe and summarize our data. I won't really focus here on the calculation of these things because very few of us do any of these calculations by hand. What I'll instead focus on is just sort of a brief conversation about 4 different types of variable. What of these measures should you report, right? If you have certain distributions or certain types of data, what is your appropriate measure of central tendency and variability? So as we know, the mean is the average score. We know that. I don't need to talk about that. What I do want to mention is that it's most useful for describing symmetric distributions. And it's frequently thought of as the balance point of a distribution. So can y'all see, sorry, you all, not y'all. Can you all see this distribution down here? The symmetric distribution. So here I'm just illustrating that this mean, which we notate as x bar, is sort of it's the balance point, right? So if you had a seesaw, it's the point at which it wouldn't teeter. This is a great place to report the mean. But this distribution and this distribution also have a mean of 3, right? So if I told you the mean of a distribution was 3, in your mind's eye, would you probably picture something that looked like this? No, you'd probably picture something more like this. And so the point here is to make sure that you're being responsible about the reporting of statistics when considering what your data look like. So similarly, so what would you want to report if your data kind of look weird? Maybe they're not symmetric. The median is one option, so that's the 50th percentile, or the score in the middle of the distribution. And we like the median because it's useful for describing what's called skewed distributions. So distributions that aren't perfectly symmetrical. Maybe they're sort of pushed to the left or pushed to the right a bit with a tail, sort of long tail on the other side. And we like it because it's robust to extreme scores. So it's minimally affected by outlying observations. A great example of this is when I taught statistics as a graduate student, I surveyed my students and I said, how much cash are you carrying on you right now? Well, the answer today would probably be 0 because no one carries cash anymore. But this was several years ago. And so most students said 0, 10, 20. And then either someone who had just come from an ATM or someone who was joking said, I have $1,000 on me. If we computed the mean of all of those students on how much cash they were carrying, what would be happening to that mean due to that person carrying $1,000? Right, I'm seeing this in the audience. Exactly, it would be inflated. So then if I told you that the mean was that students were carrying $250 of cash on them, that mean of 250 characterizes no one in my actual distribution, right? So that's an irresponsible reporting of a mean. But if I reported the median doesn't care about that 1,000. That 1,000 could be 1,000, a million. It's going to get lopped off anyway when I compute a median. So then I would say, well, the median was about $15. Does that seem a lot more representative of what I was actually trying to measure? Yes, and that's my point here. So finally, the mode is the most commonly occurring score. We use this for describing nominal data and multimodal data. So I think I have an example of that right here. So as a quick exercise for the group, suppose we introduced a new system, and to our operators who are using this new system, we administer a usability survey. And we ask them to rate the usability of this new system on a 1 to 7 scale. So because we're responsible analysts, the first thing we do is pull up a plot of our data, and we see this histogram. For the item, I thought the system was easy to use on a 1 to 7 scale. So the question I have is, what measure of central tendency should we report if we wanted to present these data as just one number? Your boss does not want a histogram. They want one number, maybe two, for you to tell them what's going on here. Well, let's go through the options together. If I were to compute the mean of this, anyone want to guess what about the mean? Like, pick a number that you think the mean would be. Here in 5, 4. Does 4 or 5 actually characterize what was going on here? No, right? How about the median? What would the median be for this distribution? About the same, about a 4 or 5. Does that score typify the distribution? No. So if I were the analyst on this, I would report 2 modes. I would say the modes were 2 and 6 because people either really found this very difficult to use or really found it very easy to use, and I should figure out why, right? Maybe it's due to experience, or maybe some operators were exposed to a condition that made the system really hard to use, and I'm not capturing that here, right? So there'd certainly be a flag raised here, but you wouldn't want to report the mean or the median. Good job, you guys passed the test. There will be a pop quiz in 45 minutes. Kidding. So moving on to variability briefly. The standard deviation is a really common measure of this. So this is the formula for it, for those of you who like looking at formulas. Like the mean, it takes all scores into account. So it's going to suffer from the same problems as the mean. If I have an extreme score, it's going to get looped into that standard deviation. So for my cash example, where that one student was carrying $1,000, the standard deviation of that distribution was probably something like 100 or 150, which is saying that on average scores were about $150 away from the mean. The standard deviation was getting very affected by that outlying score. The true spread was probably more like $5, right? So again, I don't have to tell you how to compute this because JUMP or SAS or R will do it for you, or Excel. The point really is reporting. So a quick note, you'll hear variance used a lot. Variance is just the squared standard deviation. We generally prefer reporting things in just units of standard deviation because it's not that intuitive to say, we prefer to report things in standard deviation because it's in the original units. So if I said that something had a standard deviation of 1.5 miles, that literally means a typical score was about 1.5 miles away from the mean. You probably don't get on the phone on your way home and say, hey, honey, I'm 1.5 squared miles away, right? We don't report things in terms of variance. Yeah, Jason?
What's the benefit of using variance?
In terms of reporting, there's really not a benefit of using variance, but it's helpful to note because in a lot of our statistics equations, like analysis of variance in ANOVA, it's operating specifically on certain variances that get computed. So it's kind of for your awareness thing to know that when you see this in a formula, it's just the standard deviation squared. So a quick note, we won't get too much into sample versus population notation, but if you've seen this formula before and you thought, well, I thought I've seen it before with a sigma, and I thought the denominator had an n and not an n-1. This is just the difference between the sample and the population notation. So that's just there for any of you who had that curious question pop in your mind. One very helpful use of the standard deviation is that we can take, using the mean and the standard deviation, we can convert our scores to what's known as z-scores. And z-scores mean that we take whatever our original score was, and we just turn it into units of standard deviation. So making this concrete for you, if I told you that the average female is 64 inches tall, and that I'm 67 inches tall, you immediately know that that means I'm 3 inches taller than the average. But do you know where that places me with respect to everyone else? No. But if I then told you that I was 67 inches tall, the average female was 64 inches tall, and let's say the standard deviation of that is 3, and I do 67 minus 64 over 3, my z-score is a 1. And so using that information, you could then say, oh, well, that means that in that distribution, you fall here. So I can see where you are with respect to everyone else. So that's the power of standard scores, is that we can use them to convert our scores to units that can then be compared to a distribution like this normal or Gaussian distribution. Or maybe you'll get a love letter from a statistician that says you're 3 standard deviations above the norm with a heart. And if you get this letter, that, as you now know, because you know standard deviation, this is a good thing. Okay. So beyond descriptive statistics, that was just a quick introduction, make sure we're all on the same page. They're useful and they're a great starting point for understanding your data. But as an analysis tool, they can really only get us so far. So what if we're interested in not just describing the sample that we have at hand, but also in drawing inference to some broader population, right? If I have you all as my sample, no offense, but it's not necessarily that I care about you all. I care about how you represent some broader population you're a part of. And I want to draw inference to that population, not just the sample that I have. So for this question, we need inferential statistics. You'll find many diagrams like this on the web for the general sort of process of statistics, right? That's one challenge in doing a statistics boot camp is their entire semester courses on this, right? So what do you pick in 90 minutes to focus on? So this sort of part of the diagram is what we'll really talk about today. So we won't talk too much about this kind of procedure where we sample, but we'll talk a lot about exploratory data analysis, which is actually what we just did. Exploratory data analysis is simplify and summarize your data. So the things we just went through, that's EDA, or exploratory data analysis. We get our data, we make some statement, we determine some probability, we draw inference back to the population. This is where we'll spend most of our time today. So moving to point and interval estimation before diving fully into inference. In point estimation, that simply means that we are interested in estimating some unknown parameter using a statistic. And that statistic is the thing that we compute in our sample. So again, sorry, I promise this is about the last of vocabulary. But making this concrete, the parameter is the value that summarizes the entire population. So put in one sentence, we use our sample statistic to draw an inference about the value in the population. And that value in the population is called the population parameter. So the next slide has a graphic that makes this a little bit more concrete. If this is my hypothetical population, this represents the entire population of interest I could possibly care about. The value that summarizes the entire population is called our parameter. And you'll frequently see that notated in Greek with a Greek letter. So if I'm talking about a population mean, the Greek letter is mu. The value that I compute for my sample is the statistic, right? So that if I'm computing a mean, that would just be x bar. So when you hear me say parameter and statistic today, parameter is the value for the population. We never know this value, right? We're trying to estimate it, but we don't know this value. If we did, we could pack it up and go home, right? Okay. So examples of point estimation. This is actually very straightforward. So suppose we have a new communication system and we measure the time that it takes to transmit a message. For this new system, we collect some data. We see that the average transmission time was 0.48 seconds. So our best estimate of the population mean is 0.48 seconds, right? That's our point estimate. How good that point estimate is really comes down to how good of a job we did in creating our sample, right? What if we had only grabbed kind of old, dusty, really kind of, bad communication systems? Well, then this mean would probably be biased upwards, but we wouldn't have a way of knowing that, right? So if your point estimate is off, it's probably due to something in your sample. But the calculation of a point estimate itself, very straightforward. So again, we can do this with something like a mean. We can do it with something like a proportion. So a lot of us work with data that are maybe 0, 1, like binary data, whether that's hit, miss, success, fail. Here, let's say we have a new user interface. We observe whether operators could complete a mission. And we marked that as yes, they could, no, they couldn't. We find that 90% could complete their mission. So then our best estimate of the population proportion is just 0.9. And you might think to yourself, I came here for a stats boot camp and you're telling me that my mean is 0.48, so my best estimate is 0.48. But it gets better than that. So a quick side note, if you are thinking about, well, how do I know that the mean is the best estimate? How do I know that my sample statistic is our best estimate of the population parameter? How many of you have heard of the law of large numbers? Okay, good. Fair number. Statisticians are very creative in how they name things, as you can tell. So what the law of large numbers says is that as the number of our observations increases, the difference between the sample mean and the population mean goes to 0. In plain English, what that means is the bigger our sample gets, the better it is as an estimate of the population. And this is, I think, a cool example using a six-sided die, right? So you know a die has numbers on it between 1 and 6, and if you rolled a die, and every time you rolled it, you kept track of what happened, and as you did that, you took the average. You just sort of kept taking the average. It would start out maybe as something kind of wonky. Maybe you started out with a 6 and you kept rolling lower numbers. But in the long run average, as your sample size gets bigger, it should average out to about 3.5. Right? So this is just a quick example showing that. The more times you roll a die, the closer you get to that population mean of 3.5. And this is called the law of large numbers. So our point estimate is a good starting point for quantifying a population parameter. But might you also want to know how much uncertainty is there? Well, you came to a stats boot camp, so of course you're curious about uncertainty. It's why you live and breathe. Maybe that's just me. So at this point, we transition to interval estimation, and a lot of us do this in our day-to-day analysis. So how many of you compute confidence intervals or report confidence intervals or even read confidence intervals on a semi-regular basis? Great. So I'm not going to tell you anything that you don't know about computing them. But my hope here is to sort of clarify maybe how you're interpreting them, right? Because this is something that if I had to go poll statisticians or statistical practitioners on what are your biggest pet peeves, probably think that the interpretation of confidence intervals is one of them. Has anyone ever been yelled at by a statistician on how they interpreted a confidence interval? It's okay, this is a safe space, you can admit it. I saw some nods, that's encouraging. Okay, so what is interval estimation? It provides us a range of values that have a specific likelihood of containing our population value. So it's just constructed mathematically using a sample statistic plus or minus some margin of error. And the margin of error just quantifies the degree of uncertainty in our estimate. Every time there's an election, you hear these words on the news a lot because people will try to quantify the polling numbers for each candidate. And you'll say, well, the estimate is 46 versus 54, but the margin of error is 4, right? So you'll hear confidence intervals in the news all the time near election seasons. So one example of this, you could compute a confidence interval for a mean with small sample sizes using this formula. Again, this is not a presentation about formulas. If you had a confidence interval about a mean to compute and you had a large sample, there's a formula for that. And if you wanted to compute a confidence interval around proportions, you could do that as well. But again, I said that my goal is really to tell you what a confidence interval is and why you would compute it. So this is actually pretty much the definition you'd find if you looked at a textbook. And it's that if we were to repeat the study many times, 95% of the confidence intervals that we constructed would contain the value of the true population parameter. So at this point, audience poll, how does this interpretation make you feel? Well, for those of you who really love confidence intervals, you've been doing this a long time, or you've been yelled at 20 times by a statistician, maybe this is how you feel. You're like, yep, I got it, I knew that, rock on. Maybe some of you are like, yeah, you know, I knew there was a big deal, someone made a big to-do about it, but I don't remember why. So you're like, well, maybe. The rest of you are this, right? This is why I hate statisticians. They make everything so hard. So my goal here is to really clarify what this means. So I say that 95% of similarly constructed intervals would contain the value of the population parameter. Let's see that in practice. So before I have an animation here, before I start it, so we're going to suppose the true mean, that true thing that we don't know, the value in the population, it's 5. And I'm going to take a sample from the population. I'm going to compute the mean, the sample statistic, compute a margin of error using that formula from the previous slide, and I'm going to construct a confidence interval. And I'm going to do this over and over and over. I keep taking samples from the population, compute a mean, construct a confidence interval, and plot it. And what we see is that some of these confidence intervals don't actually overlap with that true population mean. So again, if I did this, let's say 1,000 times, what we would expect is that 95% of these intervals would overlap this number 5. That's actually the interpretation of a confidence interval. It's a long-run, frequentist interpretation. We can't say we are 95% sure that the mean is this value or it's in this interval. Quite technically, the probability that the mean is in that interval is 0 or 1. It is or it isn't, right? And you can see that here. So this is, my goal here, again, is just to clarify exactly what that means. So what factors affect our confidence interval width? More variability. If your sample is more variable, you'll have a wider confidence interval. If you have a smaller sample size, you'll have a wider confidence interval. And if you have a larger confidence level, you'll have a wider confidence level. So all of these things will reflect more uncertainty in our estimate. So how many of you have been following the NCAA basketball tournament? All right, come on, guys. All right, I don't know if you can, I'm from UNC, so I followed the basketball tournament. And I had to drive during the recent UNC Texas A&M game, which was very sad, but I had the radio on. And a radio announcer, while I was, this is coming to you in real time, guys, while I was driving, a radio announcer mentioned that Texas A&M historically shot 33% from behind the arc, right? So 3-point shots, historically 33%. But in this game against UNC, we lost. I'm still upset about it. In this game against UNC, they were shooting surprisingly well. They'd hit 5 of 11 so far. So I know as a stats person, and then probably all of you as statistical practitioners, see, statistics is a hard word to say, I told you. Don't think about it when you're saying it out loud. This is the question that pops up into my head, right? Because I'm really fun at parties. I thought, well, is that statistically different, right? And after leaving today, I really hope that you all will also listen to a basketball game on the radio and think, but is that really different? So that's what we're going to find out using this equation I just showed with a binomial confidence interval. Okay, so just putting our two pieces of information down here. This is that historical proportion the announcer mentioned, and this is the 5 of 11, right? About 45%. So do we have enough pieces of information here to know whether these two values are actually different from each other? No. But if I computed a confidence interval around this estimate, could I then make a statement about whether that 5 of 11 was actually different than 33%? I could, and we do. And is it actually different? No. Our confidence interval overlaps that population proportion. So we actually would say here, radio announcer, I'm sorry, I know you were trying to make the case that they were doing really well, but statistically speaking, if I compute a 95% confidence interval, they're actually playing completely consistent with their population average. So everyone go home, make a confidence interval for your favorite sports team. Okay.
Did UNC statistically lose?
Yeah, UNC did statistically lose by like 20 points. We're not going to talk about it. We won last year, and that's all that matters. Okay. So how many of you have heard that there's something magical about the number 30 in statistics? A few nods, a few hands, right? Something is magical about the number 30, and you don't quite know what. Well, a statistician would love to tell you that there's nothing magical about the number 30, and please stop spreading that myth. It could be 32. It could be 29. It's not necessarily 30. So I want to talk about the central limit theorem, because I think this is a really misunderstood part of statistical inference. So again, textbook definition, and then we'll actually unpack what it means. So for a population with a mean of mu and a standard deviation sigma, the distribution of sample means for a sample size of n, we'll have a mean of mu and a standard deviation of sigma over root n, and we'll approach a normal distribution as n approaches infinity. So what does this actually buy us? Oh, and this about kicks in. It says as n approaches infinity, but kicks in at about number 30, sample size of 30. That's where it comes from. What it buys us is that we can perform inference even if we don't know the shape of the population distribution. So we're going to see this happen in practice. And I see a couple of faces that don't quite believe me or don't quite know what to think. So let's sort of unpack this a bit. So if we had some population of scores, they're normally distributed. Let's say it has a mean of 10, standard deviation of 2. If we take samples of size 30, or any number, but let's pick 30 here, this is just me grabbing a sample of scores from this population, and I compute the mean of it, and I plot the mean, and I throw them back, grab another sample, compute the mean, plot the mean, throw them back. The distribution of those means will be approximately normally distributed, okay? With a standard deviation equal to sigma, this 2 over root n, 2 over the square root of 30. But in case you don't believe me, let's demonstrate this. So again, same premise, normally distributed, take samples of size 30, plot the mean over and over. As we do this over and over, what do we notice about the shape of the sampling distribution of means? Is it symmetric and approximately normal? Yeah, it is. So we'll let the movie finish here. Sorry, I didn't bring popcorn. So what we notice is that the sampling distribution of means is symmetric and approximately normal. And that's great, but you might think, well, Stephanie, I'm not that impressed because we started out with a normal distribution, and then you gave me a normal distribution at the end, so where's the magic? I came here for magic. So we said that the central limit theorem allows us to know the shape of the sampling distribution, even if the population distribution is not normal. So what if the population distribution isn't normal? So here we have a positively skewed population distribution, and we're still taking samples of size 30 with replacement from that population, plotting the mean, doing this over and over again. What do we notice about this sampling distribution that's forming in front of us? It might not be perfect, but is it approximately symmetric? Yeah, it's approximately symmetric and normal. So this is the power of the central limit theorem, and this is why if we have samples of about size 30 or more, and we're wanting to perform inference on the means, the sampling distribution of means will be normally distributed. And that buys us a lot when it comes to doing statistical tools that are designed for normality. So what if our population distribution isn't normally distributed and our sample size is less than 30? This is where the central limit theorem doesn't quite kick in, right? So we see that this time we're taking samples of size 5 with replacement from the population, and we're plotting those sample means over and over. What do we notice about this as it's taking shape? I think it forms a tail here in a second. Yeah. Still kind of skewed, right? So the sampling distribution is going to resemble the population distribution. So if the population was positively skewed, your sampling distribution is going to be kind of positively skewed too. The sort of central limit theorem hasn't really kicked in yet. So we shouldn't necessarily use methods designed for normal theory here. The sort of asterisk side note is that a lot of our methods are actually kind of robust if we violate normality, but from a technical perspective, this is not a normal sampling distribution. And then finally, if our population distribution was symmetric and normal and we have small sample sizes, it's actually more or less going to be okay because the sampling distribution, as we said, will still resemble the population. Well, if the population's normal, it'll resemble a normal distribution. So it'll still be approximately symmetric and normal. Any questions on that? Do you understand the central limit theorem in a way you never did before? Okay. So we can more or less use methods based on normal theory here. So the central limit theorem, I go through all this to say, it's very fundamental to our use of what's called sampling distribution. So with a sampling distribution, we have some test statistic, and that test statistic, here the z statistic, is normally distributed. And we define what's called critical values and rejection regions. And this is going to form the basis of a lot of what we'll talk about next. But fundamentally, we take this hypothetical sampling distribution and we compare our sample result to it. And we say, this represents every value I would see under what's called the null hypothesis. So if my result is way out here, then I now think that my sample result is not consistent with the null hypothesis and I'm going to reject it. So the bottom line is that the central limit theorem allows us to perform inference on means even if we don't know the population distribution's shape. All right, so the process of hypothesis testing. I did warn you, this is the most textbook-like portion of the talk. This is the fundamental process that we go through in statistical inference, and it's essentially the process by which we go about evaluating a claim that we make about the population. And you might think to yourself, well, I don't make claims about the population. I just try to answer my research question. Well, those are one and the same, right? Because whenever you say, well, I have a requirement of this value, and I want to see if my system meets that requirement or exceeds that requirement, you are fundamentally making a statement about the population and testing your sample against that population. So you do this even if you don't know you do this. So these are the 5 steps of hypothesis testing. I think it's most useful to really focus on sort of what each one of these tells us. So our hypotheses are what's called mutually exclusive, sort of one or the other, right? One of them is sort of supported, one of them is not supported. The null hypothesis is the hypothesis of no change, no difference, or no relationship. It's the thing that says nothing's happening. The new system is not different than the old system. This factor that we had, maybe altitude has no effect on my outcome. It's the no hypothesis. And then the alternative, of course, states that there is a change, there is a relationship, there is a difference. We frequently, as stats people, break these into what's called directional and non-directional tests. So if my null hypothesis is that there's no change, and my alternative hypothesis is that there's an improvement, I posited a direction about the change, right? I said it was going to get better. It improved. That's a directional test, so it's a one-tailed test. We put all of our statistical eggs, our probability eggs, in one basket. A two-tailed test means we're not stating the direction. We say, maybe training had no effect on performance or training had an effect on performance. We don't say whether training made things better or worse. We might hope it's better, but we're not actually positing either way. I want to just take a moment to mention alpha, or our type 1 error rate. You've probably heard that this is something that you set at the beginning. You pick an alpha that you're going to compare your ultimate p-value to. The thing I want to highlight is that there's no one right answer to this. How many of you have heard that alpha of 0.05 is kind of typical or acceptable to set, right? How many of you have heard maybe 0.2 in certain contexts? Anyone have heard 0.01 before? Yeah. All of these people are right, okay? But it depends on the context. So alpha of 0.05, it's a very academic number. It actually comes from a history about 100 years ago on crop rotation. There's nothing magical about 0.05. A famous statistician once wrote a paper where he remarked, surely God loves 0.06 as much as 0.05. In defense research or exploratory research, we'll use an alpha of 0.2 because we don't want to miss an effect, right? So if we're really worried about missing the important effect of a factor, we'll set our alpha to be a little bit higher because we're not worried as much about false positives because a false negative might be much worse. In pharmaceutical research, though, they'll go the other way. They set it very low because if they're going to spend millions and millions of dollars developing something, they want to know it worked, right? So they're going to set a very small alpha because they want to be incredibly sure that the effect they're seeing is real. That drug did have an effect, that treatment did have an effect. The point here is that it depends on the context, right? So make sure that if anyone ever says, oh, you're using an alpha of 0.05, that's wrong. You should use an alpha of 0.20. Just make sure that your choice is justified by your context. So step 3 is you collect your data, you compute your test statistic. The two that we'll focus on today are the z-test and the t-test. The z-test is used when we know the population mean and the population standard deviation. The t-test is used when we only know the population mean. We do not know the population standard deviation, so we estimate it. This is mostly a minor note because if you have a sufficient sample size, the t-distribution is going to look pretty much just like the z-distribution, and we'll see that in a moment. So the next step, we've stated our hypotheses, stated alpha, collected our data, we have our test statistic. Now we want to say, what's the probability of that test statistic? What's the probability that I observe these data if the null hypothesis was true? So this is that z statistic that we've seen before. This is the sampling distribution. So we'll see this in just a moment in an example. But when we compute our z statistic, we just compare it to the range of these z statistics that we would have seen if there were truly no difference. And showing you what I just mentioned, with a very small sample size, so let's say a sample size of 4, DF means degrees of freedom. It's not really worth our time to go fully into that now, but just know that it's related to sample size. So bigger samples have larger degrees of freedom. With a very small sample, we see that T is a bit different from Z. But with a sample size of just 6 rather, T distribution starts looking more like the Z distribution. And by the time we have degrees of freedom for only 20, so sample size of 21 or 22 depending on your t-test, it looks almost like the Z distribution. So that's why I said don't get too caught up on this, right? Because with a sample size of maybe 30 or more, pretty much looks like the Z distribution. The last step is drawing a research conclusion. You've gone through all these steps, you have your p-value, and now you need to know what does that mean, right? Because that's ultimately why we're here. So if your p-value is less than alpha, you reject the null. And if your p-value is greater than alpha, you retain the null. That's just a simple decision rule. The thing that I really want to emphasize is how you communicate, right? all of the statistics in the world is worth nothing if we can't communicate it well. So this first one here, we rejected the null hypothesis saying that there was no effective training on performance, p equals 0.032. This will probably get you full credit on a statistics exam. Will it mean anything to the person reading your report? Maybe not, right? We don't go around the world thinking in terms of rejecting null hypotheses. So make sure you're stating your conclusions in plain English. Instead, just state training significantly affected performance. Individuals who underwent training had better performance, right? You don't need a p-value in there. The word significantly implies the p-value. How many of you have heard of type 1 versus type 2 errors before? Okay. How many of you get them confused sometimes? Perfect. So glad you guys are here. Everyone. Okay, so this is a sort of a truth decision matrix, right? So this is saying what the truth is. The null is true or the null is false. This is the decision that the researcher made. They retained it. Sometimes you'll hear the wording fail to reject. I don't like that wording, so I used retain. So you retain the null or you reject the null. So if you retain the null when it's true, that means there was no effect and you concluded there was no effect. That's the right call, right? You made the right call. That was the correct decision. This is what we call confidence, statistical confidence. It's the probability that you'll retain the null when it is indeed true. Type 1 error is when the null is true, but you rejected the null hypothesis. So this is sometimes called a false positive, right? And that's equal to alpha. That's the thing that we said at the beginning, where we're setting this is the risk that we're willing to take that we are going to commit a type 1 error. Type 2 error is what we call a false negative. You retained the null hypothesis, but it was actually false. That means that there was truly an effect, but you said there wasn't one, right? So confidence, type 1 error is like a false positive. Type 2 error is a false negative. And then finally, the correct decision here is that the null was false and you rejected it. So it's the probability that you're going to conclude there is an effect when indeed there is an effect. Does anyone, for extra credit with a prize that I don't have, know what the term for this is? The probability that you will reject the null when you should? Power. So exactly. Statistical power. So confidence, type 1 error, type 2 error, and power. So retain null, reject null, null true, null false. Putting this in, I think, better terms, think about it as a jury, right? So we have some truth. You've been charged with a crime. If you're not guilty and the jury says you're not guilty, that's the right call. If you're not guilty of the crime and the jury says you're guilty, it's a type 1 error, right? It's a false positive. Similarly, if you're guilty but you get off the hook, they say you're not guilty, it's a false negative. It's a type 2 error. And then finally, power is you were guilty and they did indeed conclude that you were guilty. I think some people sometimes use a pregnancy example here, where, which is also entertaining. So if you are not pregnant and someone says you are pregnant, that is a type 1 error, the error of the worst kind. And if you are truly pregnant and someone says you're not pregnant, that's a type 2 error. Also a good example. Okay, this is just a quick visualization of the relationship between power, type 1 error, and type 2 error. So if this represents my null distribution, these are all the things that I would see if the null is true. And then this is my alternative distribution. This is that there is an effect, right? So this mean maybe is 2, and this is, my null is that the mean is 2. My alternative is over here. Maybe that's my sample mean of 4. Type 1 error is this portion in the tails. It's the part of the null distribution where I would conclude that there's an effect, but the null was actually true. Type 2 error is the portion of the alternative that overlaps with the null. So here, I'm going to retain the null, but I should have rejected it because the alternative was actually true. And then finally, power is this portion of the alternative that lies past the critical values for the null. I know this is a lot to take in at once, but these slides will be available online. So if you want to look at this later, I do recommend this as a really helpful way to understand the relationship between type 1 error, type 2 error, and power, and how you visualize that. So these 5 steps describe the process of hypothesis testing. Okay, so let's dive into common statistical tests. I anticipate that several of you will have at least used one of these before. So hopefully this is relevant for all of you. So suppose I have some vehicle. And that vehicle, from the manufacturer, I know that the mean weight of that vehicle is supposed to be 14,000 pounds. This is our population mean. Suppose we have a set of n equals 35 vehicles, and our research question is, do we have evidence that our sample of vehicles is significantly different from this population? Now, if I'm simply asking, is it different? And I'm not asking, is it heavier or lighter? Is this a directional or a non-directional test? Right, it's a non-directional test. I didn't posit a direction. So as responsible analysts, we always start by visualizing and describing. So we would make a histogram of weight, and we see it's not perfect, but it's sort of unimodal and symmetric, so we're going to say that's pretty close to normal. And in our sample, let's say the mean weight was about 14,076 pounds, and the standard deviation is 102. So because we know math, we know that 14,076 is different from 14,000. But without statistical inference, can we say whether that's a meaningful difference? No. So we can construct a t-statistic using this formula. And again, use JUMP, Excel, R, SAS, whatever you like. But what this is essentially computing is, what is the difference I observed over what is the range of differences that I expected? We get a t-value of 4.43. Can we do anything with this t-value alone? No, I can't interpret this t-value. I need to compare it to something. And that thing is the sampling distribution. So this is the sampling distribution of the t-statistic for that sample size. And I shade in my rejection regions here. And what I'm saying is, these are all of the t-statistics that I would observe if there's truly no difference. So if my test statistic falls here or here, what I'm fundamentally saying is that difference could have observed by chance, but there's a very low probability that it observed by chance. So if our test statistic falls in one of these tails, then we say that we reject the null hypothesis. So here, our test statistic falls in this right-hand tail. So do we reject or retain the null hypothesis? We reject. So we obtain t of 4.43 with a p-value of less than 0.01. Just grab that out of software. So if we had set an alpha of 0.05, then we would reject the null hypothesis. Is this where you leave your research conclusion? No, right? It's not meaningful. So you would say our sample of vehicles is significantly different, or you would specifically maybe say significantly heavier than the population of vehicles. You might think to yourself, okay, I got that. We're comparing one mean to a population value. What if I have two things I want to compare to each other? So we're not now just interested in comparing our sample to the population, but instead in comparing two things. So maybe it's a new system versus an old system. Maybe it's variant A of something against variant B. Maybe you care about human factors, and you're comparing demographic groups in some outcome variable. So my background's in applied statistics, mostly for human data, so I do apologize. A lot of my examples are operator. I don't apologize, right? So suppose we're interested in comparing a new helmet, right? We have an old helmet, we have a new helmet. We want to know if it improves comfort, right? Operators need to wear this. We want to know if it's going to be more comfortable. So we do a test. We assign 20 people to use the old helmet and 20 people to use the new helmet. We observe how long it takes for them to take it off. That's our measure of how comfortable it is. So we're going to compare those two means to each other. The mean number of hours for people wearing the old helmet and the mean number of hours for the people wearing the new helmet. Everyone on board with our OT here? Good. So we start by describing and visualizing. So here we compute a mean, standard deviation, and sample size for both groups. And this is one of my favorite visualizations for continuous data, as a box plot. So this is showing the central tendency and the spread for the old helmet and the central tendency and the spread for the new helmet. So just eyeballing this, does it look like the new helmet is better? Yeah, we see so far. Yeah, that looks pretty different, and the spread of the scores, that kind of, the whole block looks higher. But can we say yet whether that's significant? No, because the word significance in statistics is reserved for one purpose only. That's talking about p-values, and we don't have one yet. So we're gonna go get one. So we construct the t-statistic using this formula, or software, because it's 2018. And just to note, this pooled variance here is just this formula. So we pool our sample variances for each group together into one estimate. There's a formula that doesn't do this in case you needed it. we get a t-value of 3.86. Again, given up the magic by now, but you know that this 3.86 doesn't mean anything by itself. We compare it to a sampling distribution to determine, was this likely due to chance? So here, we see our test statistic and we see our rejection region. What do we notice about this rejection region versus the one I drew before? It's one-tailed. And I know I went through the last slide relatively quickly, but from my research question, why am I using a one-tailed test here? Improvement, exactly. I explicitly want to know, did it improve? Not did it get worse, not did it remain the same, but did it improve, right? So here, because I didn't just say, is it different? I said, is it an improvement? That's a one-tailed test. Awesome. So I lump all of my rejection region over here, and it doesn't really end up mattering because we see that our test statistic lies in that rejection region. What decision do we make about the null hypothesis here? Do we reject or retain? Reject, exactly. And again, I know the wording is cumbersome, but the reason we reject is because this picture represents all the values we would see if the null was true. So what we're saying is, well, my value's all the way out here, so it was very unlikely to occur if the null was true. So I'm going to reject the null. I don't think the null is true. So how many of you either work with, for proportion data, how many of you work or kind of write reports for binary outcomes? So 0, 1, hit, miss, success, fail, right? Coin flip, heads, tails. So we can do a test of one proportion as well. Earlier we saw how to do this just using a confidence interval, but this is an approach using p-values. So I have found myself in this world a lot at IDA in the systems that I work on. So specifically with things like missile launch and torpedo hit. So we are frequently interested in estimating some underlying probability of an event. So what is the probability of successful missile launch? What is the probability of a successful torpedo hit? What is the probability of a successful message transmission? We generally do prefer continuous metrics, but in some cases we can't avoid a binary outcome. Sometimes it doesn't matter how close the torpedo got. What matters is if it hit or not. And so we don't have a continuous outcome we can use like miss distance. Instead, we have to use that 0, 1 outcome. And we have tools designed for that. So to do this, we'll use what's called the binomial distribution. And for the binomial distribution, these criteria must be met. Everything yields a success or failure. One of those two things happens. Each event is independent, or sometimes you'll hear this called memoryless, like a coin flip. So if I flip a coin and it's heads, has absolutely no bearing on what my next coin flip will be, right? It could just as likely be heads or tails. And the underlying probability is constant across events. And extending the coin flip example, what that means is that if I flip a coin, what's my probability of heads? If you flipped a coin right now, what's the chance you'd get a heads? Not a trick question, 50%, thank you. And if I flip it again, it's 50%. But what if halfway through my coin flip, someone ran up, swapped my coin, and now it's weighted, and it has a probability of heads of 0.7? That's a problem, right? So for the binomial, we assume this underlying probability is constant across events. It doesn't change. So just like we used a z statistic before for means, if we can invoke the sort of normal approximation for this, then we can construct a z statistic for proportions. So we have a proportion called p hat. That's just the number of successes over the number of trials. So how many times did you succeed divided by how many times did you try, right? I got Texas A&M got 5 3-point shots and they attempted 11 times, right? So P is 0.45, 5 over 11. This is the formula for the standard deviation. We put this all together using our test statistic Z. So we can follow the same process as before for a proportion event. So here's our scenario. We have a system for transmitting messages, and some legacy system had a probability of 0.8. And that was the probability of a successful transmission. So any time a message went out, there's an 80% chance that it would successfully transmit. And now we have a new system. And during the OT of this new system, we observed that 38 of 50 messages transmitted successfully. Our research question is the new system worse than the old system? And you might think to yourself, well, it's kind of a weird question to ask. But sometimes we don't actually need a new system to be better. Sometimes we just need it to not be worse, because maybe it's improving some other thing that was problematic, right? So for some systems, it might be the case that we don't necessarily need it to be better. We just want to make sure it didn't decrement performance. Because like I said, maybe it was introduced to solve some other problem. And we're just doing our diligence, making sure that something else didn't get unexpectedly affected. So if I ask this research question, do I have a one-tailed or a two-tailed test? One-tailed, exactly, because I've posited the direction. So just grabbing, just sort of, word probleming this, grabbing out my relevant quantities. I had 38 successes, 50 tries, 38 over 50 is 0.76, and that population proportion was 0.8, right? The legacy system. So nothing too magical here. I get a z-statistic of negative 0.7. Can we conclude that the new system is worse than the old system? No, we can't. We know, again, because we know math, that 0.76 is lower than 0.8. But is it significantly lower than 0.8? It's not. And so in this situation, we would just say we can't conclude that the new system is worse. We could just say, our evidence is that it's consistent, right? But we certainly can't conclude that it's worse. Okay, so we'll spend our remaining time on the general linear model. So the general linear model is the framework that sort of captures a lot of what we just talked about. So making that a bit more concrete, it's general because it's widely applicable to estimating and testing hypotheses about parameters. It's linear because we have some linear function of the parameters. And it's a model because it describes a relationship between some outcome variable and one or more predictor variables. So everything we've discussed so far has been one outcome and one predictor. And this framework allows us to have one outcome, or potentially more, but we'll keep it at one, and a set of predictors. And we can evaluate their simultaneous impact on our outcome variable and sort of look one by one what's happening. So in its absolute simplest form, the GLM can be expressed like this. We have some outcome variable that's a function of an intercept, some x variable, the slope. This is the intercept, this is the slope. Some slope governing the strength of the relationship between our predictor and our outcome. And then some amount that we can't explain, right? And I think this is more helpful to understand in picture form, which we'll do in just a moment. So for this very straightforward case of just one response variable, one predictor variable, you'll hear the phrase simple linear regression used to describe it. So with two continuous variables, we can plot our data. So plot your x, plot your y, and just look at a line of best fit through those data points. So this is a relationship between the weight of a car and its miles per gallon. So for those of you who drive like a Ford F-150, you're probably way down here, right? Enjoying your life, but not getting very good MPG. And maybe those of you who drive a smart car are way up here, right? You're getting a lot of miles per gallon. And we could plot a line of best fit through this that allows us to then predict, well, if I then take my car and I want to compute its weight and see what my expected miles per gallon is, we can get a regression equation that tells us that relationship. And so that's exactly what we can do. Here's our same scatter plot as before, but we plot what's called a line of best fit through it. And we do this using ordinary least squares. And so here, the beta is just the slope of this line. Back from high school, you remember the phrase rise over run? That's all this beta 1 is just the slope. Y is just the actual value of y. And then there's residual here is the discrepancy between what I observed and the predicted value. So for this person, or for this car rather, our regression equation is doing a very good job of predicting that value. For this car, there's a bit of a bigger residual. So there's a bigger difference between the predicted value and the value that I observed, right? And so these are our residuals. And this is just ordinary least squares. Regression, we have two continuous variables. We plot a line of best fit through them. And what line of best fit means is just that this line minimizes the sum of these squared residuals. So if I were to draw a line that was just flat, I would have a terrible line, right? Because I would have all these very big residuals. All the data points would be far away from that regression line. Okay. I have this slide up here mostly sort of as for your awareness. Because when you do design of experiments or when you do any kind of modeling that in the GLM, in that flexible framework, this is how all of the models that we expressed before could be parameterized. So all I mean by that is, we talked about a t-test. How many of you have heard of an analysis of variance, an ANOVA? Right. We could take an ANOVA and we can express it using this same notation. We could express an analysis of covariance. We could express a multivariate analysis of variance. The point here is that this matrix notation is flexible, and it allows us to specify a variety of models flexibly in the GLM framework. So this is mostly here for your awareness in case you come across this kind of sort of notation. Once we move to more complex models, we frequently move away from what's called the scalar notation to this matrix notation, because it allows us to more compactly represent things. And for those of you who have used maybe JMP before to do a DOE, and you input a design matrix, that design matrix is just X, your X term here. Okay, so you all have computers. You can all Google general linear model. But I think some of the more misunderstood things about the general linear model are its assumptions. So this is why I wanted to make sure to touch on these very briefly. So the assumption of homogeneity just means that there's constant variance around any value of the regression equation. So if that's violated, picture in your mind's eye that same plot we just had with weight and miles per gallon. If homogeneity was violated, then some parts of our regression equation would be doing very well. You'd see really small residuals around the line. And then for other values, there'd be very big residuals, right? And what that means is that there's not constant variance around the regression line. Our regression equation is doing poorly in some parts than others, and that's systematic. Independence of errors is a big one. So I think this is best understood with examples. So things that could violate independence, if you're doing human factors research and you have operators, and one operator gives you multiple observations, their errors are not going to be independent, because I'm more like myself than I am like Jason. And so my observations are probably going to be correlated within me. And so that's going to result in errors that are not independent. So the note here is that if this is violated, make sure that you check your sampling or your design. This could also happen with something like operator learning effects. If you are measuring an operator over time, and let's say they're shooting a gun or shooting something and you're measuring their miss distance. If you're an operator and you're measured 10 times doing this task, what might happen to you over those 10 times? You might get better, right? So your miss distance is going to decrease as a function of time. Well, that means that those errors are no longer independent, and that's a problem. Linearity just means that the expected value, or the mean, is the linear function of the parameter. So this is linear, but putting x to the beta power is not linear, because it's, quote, not linear in the parameters, where the parameters are beta 0, beta 1, and so that's all that means. Existence is a very boring one. That just means that the mean and the variance of that distribution exist. You can take that piece of information, throw it right back out of your brain, because you're never going to have to check that assumption. But it does exist. So for those of you who have done a regression before, how many of you have heard about the fact that normality matters with a regression? Yeah, you're like, sure, normality matters. So I put this in here because I hear this one confused a little bit sometimes. So the assumption that we have to make if we want to perform inference, and what I mean by that is if we want to compute p-values for each of the effects in our model, then we must make one final assumption, and that assumption is called Gaussian errors. So again, let's just unpack this briefly. So if this is my outcome variable, let's say my outcome variable is height, and let's say this is height of human beings. We see two peaks here. We'd call this bimodal, right? Does this look normally distributed to you? No. But does the outcome itself need to be normally distributed? No, it doesn't. So not overthinking this, if you saw that the height of human beings looked like this and you saw two distinct peaks, why might this be? Males and females, right? Males and females have sort of different means and different peaks. So maybe this is actually it was not intentional that this turned pink and blue. These were the plot default colors. But the distribution of women their height looks like this. The distribution of males is over here. So if I form a model where I predict height using gender as a predictor, or sex, sorry, biological sex. So if I form a model using biological sex as a predictor of height, and I plot my residuals are actually normally distributed. So what this means is that the assumption that we actually need to make, and we can verify this using our software of choice, is that our outcome conditioned on the predictors is normally distributed. So it doesn't matter that height is not normally distributed. What matters is that height conditioned on my predictor variable is normally distributed. And we can check that using the residuals. So would we all agree that this looks approximately normally distributed? Yeah, close enough, right? You could evaluate this using something in software like a QQ plot or whatever your favorite tool is for evaluating normality. But I wanted to make sure to mention this here because we know that normality matters, but it's specifically normality of your errors. So these 5 assumptions, when I took a class in statistics, the instructor used the moniker Heil-Gauss to kind of help you mentally organize those pieces of information. So homogeneity, independence, linearity, existence, and Gaussian errors. Those are your 5 assumptions in a regression to be able to both perform estimation and statistical inference. Any questions on this? Feel good about telling people when they're like, oh, we can't do a regression, the outcome's not normal, and you're like, just kidding, that doesn't matter, let's check the errors. That's what you're going to say, right? So this is just a quick example clarifying what the effects in a multiple regression or a general linear model mean. So I have some system with a new user interface. The user interface was designed to be simpler and clearer to operators. So I just want to know if the new system improves their reaction time compared to the old system. And what we also ask operators, because we want to collect some demographic data, we have them rate their experience on a 1 to 7 scale. We could have asked them their number of hours of experience. Either way, the point is we have some metric of their experience. So we have as factors the system, new versus old, their self-rated experience, and then this interaction effect between system and experience. So main effect, interaction effect. So in multiple regression, instead of just having one hypothesis test as we did before, we actually have a hypothesis test for each effect of interest. So we'll have a hypothesis test for this term, and this term, all within one model. But what I want to focus on is why would you care about main effects and interaction effects, specifically interaction effects. So let's say I just look at what's called the main effect of system. So not caring about experience for a moment, I see that using the new system, reaction time decreases. That's a good thing, right? New system looks like it's working, as we intended. Now I look at ignoring system, let's look at experience. And I see that more experienced operators react faster. That seems consistent with what we might expect, right? More experienced people are a bit quicker to react. They're more used to it. But then I plot the interaction effect. And I see this. And walking through this together, what this is actually saying is that the new system, regardless of operator experience, the reaction time was quicker. And in the old system, experience mattered a lot more. So in this old system, you had to be a lot more experienced to get a good reaction time. And if you were new, your reaction time really suffered. So this is an important interpretation because this is probably why you've heard a statistician say their 2 favorite words. It depends, right? There's a reason. If I asked you, what is the effect of system on reaction time, you would say, well, it kind of depends on your experience. Because if I was already a very experienced operator, the new system helps me, but not by a lot, right? I only see a small change in reaction time for experienced operators in new versus old. But for less experienced operators, I see a very big change in reaction time from the new versus the old system. This is a conclusion that someone could really care about because it allows them to make a decision about the utility of this new system. Now, it would be very unfortunate if we had only had very experienced operators, right? Because in this system, would have made it look like the new system barely mattered. But this is why you would interpret an interaction effect. And indeed, in the presence of a significant interaction effect, these main effects become a little bit less meaningful. You'd really want to spend your time interpreting the interaction and not the main effects. So the conclusion, the new system improves the reaction time overall, but particularly for individuals with low experience. So to finish the end of the content before I give your brains a break, and we just close with a few kind of kind, gentle, soft statistics tips. I have this mostly here for your awareness. So we talked earlier about using a test of a proportion. If you have that 0-1 binary hit-miss data, you can also model that in a regression framework. And that might sound weird at first, that you could model a 0-1. But we can do that using what's called the generalized linear model. And if it makes you feel better, the person who came up with the nomenclature, general versus generalized, does feel bad about it. I read an interview where he said, I do kind of feel bad about it. It's unfortunate. So two common examples that you've probably maybe heard of or heard someone say are Poisson regression and logistic regression. And logistic regression is where I spend a lot of my time, and it's a very common situation. We have some binary outcome. So this is just showing you the possibility that you have in the generalized linear modeling framework. You can use all of these, quote, link functions. They're at your fingertips to map your predictors onto some outcome. We're only going to focus on one of these, and it's called the logit. So if we have some mean that's expressed using a linear predictor, and we have a link function that just describes a relationship between a mean and the predictor. So this is just saying that my mean's a linear function of beta and beta 1. That's all this is saying. The normal GLM, the one that I just presented, can be expressed in this way, just using the same expression with what's called an identity link function. And all identity link function means is that we're not doing anything to transform it. We're just using the mean, right? But that's not why we're here now. We're here to hear about logistic regression. So with logistic regression, we're just going to change out this link function. Instead of it just being identity, we're going to use that logit that I just highlighted in the previous table. So essentially, you can even mentally sort of skip this part if you'd like. The relationship now is going to be through this logit. So instead of having y on this left-hand side, I have my p hat, which is my proportion, and I'm modeling the logit of it, because that allows us to preserve the relationship between our predictors and our outcome in a regression framework without trying to do something like predict 0-1 as it is. So this is, I should have put a meme here. If you try to fit a line through 0-1 data, you're going to have a bad time, right? This isn't telling you much. So just visualizing what that just says don't do it. Visualizing what the logit does is we're just going to be mapping between our predictor, and instead of modeling the 0-1, we model the probability of something being 1. So this is saying as my predictor increases, so whatever this predictor is, experience, my probability of an outcome increases. So maybe my probability here, maybe my outcome is mission success, 0-1. So if I have a 0-1 for mission success, and this predictor's experience, it's just saying that as experience increases, the probability of mission success increases. And this is what logistic regression buys you, is the ability to model in this way. Okay, this is just a summary saying that the general linear model is a very flexible framework that encompasses things like the t-test, the analysis of variance, regression, and the generalized linear model allows us to extend to a variety of frameworks using what's called link functions, including the logistic regression, the Poisson regression, and the multinomial regression. Okay, a few closing tips. How do we feel? How do we feel about the Google slide of statistics is boring or hard? Did it at least change you on statistics is boring? Hard to say. It's still hard to say, right? Now what's going to happen is you're going to be having a conversation with someone about statistics, and you're going to think of that as you say it, and you're going to look about as stupid as I have standing up here tripping over the word statistics. So you're welcome. My 3 closing tips are, first, make sure that the test that you select reflects your research question. Carefully consider outliers, and follow good practices of data visualization. So each of these 2 is just one slide. So the one that I really want to just tell you about is really thinking carefully about your test reflecting your research question. So when we are selecting the correct test, there are important questions to keep in mind. These are some of these questions. So far with all of our examples, I kind of gave a very explicit purpose that we had. And you might think, well, I'm interested in knowing if there's a difference. And then I'm going to ask, well, a difference in what? A difference in the means? or a difference in variance, or a difference in the median? What is it that you care about? And if we go back to Google, our best friend, and we're feeling lucky, we type this into Google. Boy, those psychologists really care about getting the right statistical test. We click I'm feeling lucky, we see where Google takes us. How many of you have stumbled across a chart like this before, an eye chart like this, right? Okay, so here's one approach. You could follow your way through down the yellow brick road of this eye chart and try to end up at the right test. Maybe you found this one when you were feeling lucky. Or finally, maybe you found this one. I will admit that these flowcharts can be useful. But when you adhere sort of strictly, or maybe a little bit sort of too much to their use, it can derail you from thinking about the question you are actually trying to answer. So this is just an example of flowchart reasoning gone wrong. So I have a continuous outcome variable. I want to know if there's a difference between source A and source B. Two things, just calling them source A and source B. Maybe it's a simulation, right? In the defense world, we do a lot of modeling and simulation. Maybe I have a simulation from company A and a simulation from company B. And I want to know, are the simulations from company A and company B telling me the same thing or not? So what is a problem that you notice maybe, given what I just soapboxed, on I want to see if there's a difference between source A and source B? A difference in what? So we don't know. We go through a flowchart. So one-third journey through a flowchart later, we say, difference in means. I'll do a two-sample t-test. And you plot the mean for source A, and you plot the mean for source B, and you get your t-statistic of 1.13 and a p-value of 0.26. And if we set an alpha of 0.05, what would we, or let's say we'll set an alpha of 0.2, we'll be generous. If we set an alpha of 0.2, what do we conclude about the null hypothesis here? We retain it, exactly. We retain it because our p-value, our probability value, says that there's about a 26% chance that I would have observed that difference if there were truly no difference. I'm not comfortable with saying that it's different. But what if we had actually cared about a difference in spread? So here I just made a bar graph, right? I just plotted the means. But what if it was a difference in spread that I cared about? Maybe the simulation from company A is producing about the same mean as the simulation from company B, but company B's simulation's a lot wider. Gives me a lot more variable results. Is that something I might want to know about? Yeah. And so this is an example of flowchart reasoning gone wrong. I journeyed through a flowchart, I arrived at a two-sample t-test, but I completely missed this difference in spread that would have potentially been meaningful for me to know about. So this is sort of my buyer beware on the eye charts for picking the right test. So that's what I just said. Okay, one slide on outliers. This is from that same CARS data set, actually. You'll notice here that I don't have a lot of data points. So here, showing two things at once, actually. Look at the R-square value for this model. It was 0.28. By just reducing this data set by these two outlying observations, my R-square value goes to 0.7 something, I think. It's a very big difference in my explanatory power. But should we just go through our data set and click delete on things that look funny? No, we shouldn't, right? The point is to carefully consider outliers. So when you see an outlying observation, one, make sure that you look for them, because if you had just plotted this line and never looked at your data, you could have missed that. And you would have thought that your model wasn't very good because your R-square was only 0.2 something. But with those two outlying observations removed, it was 0.7. Now that doesn't mean you should just remove outliers if they improve your story. What it means is that if you see these, you should say, where did those come from? And then I tell you, oh, some undergraduate entered this data. They meant to type 20, instead they hit 2, right? Happens all the time. Well, then you can delete those safely because they're not valid data points. But if those are valid data points, you can't just delete them. You need to consider where did those outliers come from and what does that mean? And just note that with a small sample size like this one, just a few outlying observations can really change your results. So make sure you look for those outlying observations. And then the final tip, just make sure that when you're visualizing your data, when you're communicating your results to people, you match the right graphic to the thing that you are displaying. So what I mean by that is if you have a discrete variable, let's say you have variance of a system. Maybe it's the JSF. You have A, B, and C variant. Heather doesn't like that example. And we just have counts here. We're counting how many A there were, how many B there were, how many C there were. For a discrete variable, you can also use a pie chart, or can you? Don't do it. Don't use pie charts. Some people like pie charts. The only acceptable use of pie charts is visualizing how much pie was eaten at DataWorks yesterday. That's it. Okay, that's it. The reason why is because there's no real good reason to use a pie chart instead of a bar graph, because a bar graph gives you an axis, it helps you discern relative amounts, it does everything that a pie chart does, but it does it better. So don't do it. Unless you make a pie chart of how much pie was eaten at DataWorks and tweet about it. We need another pie to appear. Not just, I guess you can do it with cake. There was cake today. One continuous variable. If you like looking at both kind of the location and spread, use a histogram. Or if you want to express it more succinctly, box plots are nice. So we can both visualize our central tendency. Here this line is our median and our spread. Finally, two continuous variables. If you're looking for a relationship, then make a scatter plot. If you want to be able to talk about some kind of linear prediction or nonlinear prediction, make sure you add a line of best fit to it. And then finally, if you have two continuous variables and you're looking for a difference, you could do several things. I, again, like these box plots as a way to both compare the groups in terms of their central tendency and their spread, because as we know from the source A versus source B example we just went through, sometimes we care about one or the other, sometimes we explicitly care about both. Thank you all very much for your time. If you have any remaining questions, I think we have -1 minute remaining. So I am here if you need anything. Otherwise, thank you for coming.